In this presentation, we are going to look at matrix calculations that are required for looking at walks and cycles when we're looking in graphs. So let's look at an example here first off. Let G be the simple graph on the vertex set V of G equals 1, 2, 3, 4, 5, and it has the following adjacency matrix. What we're asked to do is draw G, and then for each pair of distinct vertices of G, find the number of paths of length 2 between them. Okay. Then we are asked to compute the matrix a to the power of 3 and explain what the entries of a to the power of 3 says about graph G. And then finally, for each pair of distinct vertices of G, find the number of paths of length 3 between them. So let's go at that. So first off, what we are asked to do is to draw G. Now, essentially, I'm going to sort of speed things up here. I'm just going to present the answers there. So this is the this is the adjacency matrix, and this will be the corresponding graph there. Okay, so vertex 1 is connected to 2, 3, 4, and 5. All the other vertices are just connected to vertex 1 only. So what we have there is that sort of cross-shaped graph. Okay, so moving on from that, what we're asked to do is for each pair of distinct vertices of G, find the number of paths of length 2 between them. Now, what we have to do here is to find the number of paths of length 2 is to go to so essentially it's based on the adjacency matrix. So paths of length 2, what we have to do there is compute the adjacency matrix. We have to square it. Okay, so essentially what happens when you square this matrix, as in multiply it by itself, you would get this matrix down here. Okay, now importantly, what we have to do is remember that we're asked for the number of paths of length 2. So a path must must have distinct a set of edges and a set of vertices. Okay. So first off, what is this down here? What do we have down here? So it's paths of length 2. What I want to sort of illustrate is this is the number of walks of length 2. That is what we have here in this matrix a to the power of 2. Let's just sort of reacquaint ourselves. I'm just going to skip forward a bit with the definition of a path. So I'm just going to sort of skip down here a bit because a path is an alternating sequence of vertices on edges of the form such and such, and all of the vertices and the edges are distinct. That's an important matter here. So we're told we're talking about walks when we're talking about a to the power of 2. We're asked about paths. So we must not include any of the diagonal entries there. Okay, so essentially, just look in the context of walks, there's no restriction on walks, there is a restriction on paths. So for example, a walk that starts at 1 and ends at 1 that of length 2 would have something like that, go there and go there. So go up to vertex 4 and come back to vertex 1. Likewise for each of the other going through any of the other vertices, go down to vertex 2 and then come back. So there are 4 walks of length 2 that start at 1 and end at 1. Likewise, there's a corresponding walk start at 4 and go down to 1 and then come back to 4. So those are all the diagonal elements there. A path of length 2 is for each pair of vertices, there's only one path between those vertices. So, for example, 3 to 1, and then down to 5. So there's only one possible way you can have a path between 3 and 5 that has length 1. Likewise, 3 to 2, you have to go to 1, and then go to 2. Okay. So, for each pair of vertices of G, find the number of paths of length 2 between them. So, it is the off-diagonal elements of A to A squared. So you change everything on the diagonal to 0. Okay? Because that is not a path, it is just a walk. Okay. So compute the matrix A to the power of 3 and explain what it says about the entries of G. Well, let's go to that one first. Then the entries in A3 show the number of walks of length 3 between any of the vertices. So again, if you were to multiply A squared by A, you will get A cubed. So there's a lot of matrix calculation involved in this. It's actually quite tedious, but you can get through it pretty quickly. It's once you have a couple of the calculations done, you can sort of replicate them. And when you multiply A squared by A, you will get that matrix down there. So it's not possible. For example, starting at 1, a matrix must, if a matrix starts, if a walk starts at a particular vertex, it must ultimately end up back at 1. Okay? So, for example, we started at 3 there, it went to 1, then down to 5, and then back to 1. There's no possible way you can get a walk that starts at any of the other vertices. It will always end up at 1. Likewise, if we have a start at 1, it can go up there, it can go down here, and it can go somewhere else. So it can go to any of the 4 matrices now. So I'm just going to go down there to 2. So starting at 1, there are 4 possible walks of path 3, of length 3, that are possible there. So if it starts at any of the other matrices, it will end up at 1. Or any of the vertices, it will end up at 1. But if it starts at 1, it can end up go to any of the other 4 matrices. For 4 vertices, sorry. Now, I mentioned previously that this matter about a path is an alternating sequence of vertices and edges. And the vertices and edges are all distinct. Now, the question was, for each pair of distinct vertices of G, find the number of paths of length 3 between them. Now, it's not possible to have a path of length 3. A path must not use the same edge twice. It must not go to the same vertex twice. So it's actually not possible to have a path of length 3 for this graph. Again, ultimately you have to reuse the same edge or same vertices sooner rather than later. So it's possible to have a walk, but it's not possible to have a path. Okay, that ends our presentation.